So thank you, Dr. Dharmendra, for kind introduction. And also I'd like to express my sincere thanks to the whole organizing members of this International Conference on Research Methodology, ICRM 2023. And in particular, I'm thankful to the whole administration of Dr. Shakuntala Mishra National Rehabilitation University and Science Tech Institute run by Manraj Kuar Singh Educational Society, Lucknow. And also, I'm thankful to Dr. Sushil Kumar Singh, who has given me this opportunity to talk about my research work on this platform. So the topic of my talk is doped and co-doped ZnO nanostructures, sol-gel synthesis and their characterizations. So here, if we look at this co, so C has been intentionally put small. So here this co means along with the dopant, another dopant is available. So this co does not represent cobalt. So that's the caution. So with this, I'd like to begin. So this is my university. It is a NAC A+ university and situated in the heart part of Jaipur. And if you have ever chance to visit Pink City, that is Jaipur, so do come to our university and visit our laboratories, and you can have a glimpse how we are working on different problems in terms of research and innovation. So the contents which I'm going to cover in this talk, even though the conference is on research methodology, so I'll try to give a more push on research methodology part rather than sharing more of the results of my findings. So I'll try to give say general overview because in the morning when I was attending this inaugural session, so I got to know that people from multiple background, they are attending this conference. So I'll try to keep things in more generalized form rather than describing the things in say specific manner. So my whole research is centered around only one term. It is frugal. So frugal research means cost effective. So whatever we are doing, so we are trying to minimize the cost, and with minimum cost, how we can produce the better results. So that's the motto with which I am doing research at my laboratories. So contents will be talking about a little bit basic things about wide band gap semiconductors. ZnO is one of them. Another wide band gap, very popular wide band gap semiconductor is titanium dioxide. And then we'll talk about slightly doping and co-doping, what these terms refer to, and then certain systems which I actually picked for carrying out some research work, and then titanium dioxide also will pick up slightly, and then will describe the summary of overall findings. So when we talk about doping, so doping is if we take say general background for this term doping. So doping is not taken in a very positive sense. Currently, say cricket World Cup is going on, and if we talk about other sports, so if you talk about doping connected to sports, so it's a prohibited thing. So it is not taken in a very good sense. So for common understanding, I'm talking about doping. So that doesn't mean I'm talking about some prohibited terms. So I'm going to take up this doping term particularly associated to semiconductors. So in semiconductors, doping is taken in a very positive sense. So in fact, it is running a big world of technology. It is all because of say suitable dopants used in semiconductors, pure or intrinsic semiconductors. So they have given rise to multiple technologies. They have given rise to multiple innovations. So I'll be talking about doping in semiconductors, not doping connected to the sports. So what wide band gap semiconductors are, I've put two semiconductors, zinc oxide and titanium dioxide. They are very popular. Wide band gap, their band gap is slightly larger than the conventional semiconductors like silicon or germanium. So they have the wide wide band gap nearly in the range of 3 to 3.5 electron volts. Both of them are having some common features. First thing is they both are multifunctional. Multifunctional means simultaneously multiple features can be obtained, can be seen in these semiconductors, and they produce, particularly when we move to nano regime. So today is the word of nanotechnology or nanoscience. So when we move to the nano dimension, particularly in these materials, so we obtain diverse variety of nanostructure. So and every nanostructure demonstrates some kind of special feature or quality. They both are non-toxic as well. And there is a popular term in these days which is called as photocatalysis. So for photocatalysis, they both are very good materials because of their wide band gap semiconductor and because of the possibility of tunability of their band gap. Tunability means the band gap can be changed, can be reduced or enhanced by using suitable dopant. So we can cover a large range of band gaps. So when we move to the photocatalytic behavior, band gap plays a crucial role. So, and their synthesis is very cost effective. As I mentioned in the beginning itself, that I am concentrating upon frugal research. So we cannot, I'm trying to pick up some material which is very cheap, very simply available at very low cost. So if we compare in between zinc oxide and titanium dioxide, so titanium dioxide is slightly costlier than zinc oxide. Preparing zinc oxide is very easy. So what doping and co-doping is, that we'll be talking about in general. So doping means introduction of some, say, intentional impurity into an intrinsic semiconductor. So intrinsic semiconductor means pure semiconductor. So if we pick up a pure semiconductor and introduce some kind of impurity, here again, I would like to mention specifically when we talk of impurity. So impurity addition is not taken in a good sense in common practice. But here in semiconductor, when we introduce some impurity into a semiconductor, so semiconductor, its features are changed, they are impacted. As a result, we get multiple suitable things in terms of their properties and in terms of their caliber to convert themselves into devices. So that is why doping is a very important phenomenon, important, say, process in connection to the semiconductor industry. So which dopant should be chosen? We talk of p-type semiconductor, n-type semiconductor. So which dopant should be chosen? So it is a very careful exercise. So how to choose a suitable dopant? So that is a very careful exercise. We need to look at the say electronic distribution of the dopant and the host material, and also we look multiple other parameters, and then we pick up a suitable dopant. And that dopant has the possibility to impact multiple features. Particularly, I'll be talking about, say, optical and magnetic features. How are they impacted by utilizing a dopant into these wide band gap semiconductors? So bipolar doping is sometimes very good and very easily available, but sometimes it's difficult in certain semiconductors. So bipolar doping means when we talk about doped semiconductors, so we generally talk about p-type and n-type semiconductor. So p-type semiconductor and n-type semiconductor, they can be formed by using a suitable dopant in an intrinsic semiconductor. For example, if we take silicon, so if we dope a pentavalent impurity, so the silicon material will be converted into n-type semiconductor, and if we dope a trivalent impurity into silicon, so it will become p-type. So meaning to say, silicon can be converted into p-type as well as n-type. So this is called as bipolar doping, means both the polarities or both types of semiconductors can be prepared by doping. But in some semiconductors, it is difficult. For example, if we talk about ZnO, so zinc oxide is a semiconductor which is n-type inherently or by its own nature. but converting it into p-type is still a challenge. Numerous say large number of studies or large number of experimental things been carried out, but it has yet not been achieved in a stable form. So that's the challenge with certain semiconductors. So it was seen that co-doping can help us. Co-doping means along with one dopant, another dopant, if it is added. So what would happen to that particular material? So the objective was not to achieve, say, bipolar doping. At the same time, objective was also to achieve some other special features. So what will happen to the material features if we use a co-dopant? So co-dopant, just an example is given here. If we talk about gallium nitride, so if when Mg is doped into gallium nitride, so carrier concentration becomes of the order of 10 to the power 17. And when a co-dopant is used, so the carrier concentration goes up by a very large order of magnitude. So that means addition of co-dopant can further enhance or can further change the material properties or semiconductors properties. So co-doping is used for multiple regions in semiconductors, particularly for enhancing the dopant solubility, because sometimes when you use a dopant, so it doesn't get dissolved in the material, so another dopant helps in dissolving that dopant material in the host material. And it also enhances the activation rate, and also the carrier mobility. That's the prime factor. Carrier mobility and carrier concentration, they are hugely impacted by co-doping. So co-doping is generally categorized into three forms. One is called as fully compensated, partially compensated, and non-compensated. So compensation means whatever impact has been created by a dopant, can we compensate that impact by using a co-dopant? And also compensation refers particularly for charge. So if you have added one, say, positive ion into the matrix, so can we add a negative ion simultaneously so that the charge compensation has been maintained? So fully compensated means all extra atoms or all impurities which you have added into a semiconductor, so their charge is fully compensated by the charge of the co-dopant. And partially compensated, you are able to compensate some charges, and non-compensated, then you are not able to compensate the charge in a complete sense. So that's the idea of co-doping. So, and the method particularly which I utilize is sol gel method. So sol gel method, I've talked about frugal research. So frugal, uh, this is the most frugal method for creating or developing nanomaterials, particularly of metal oxide semiconductors like zinc oxide or titanium dioxide. So we always begin with some starting compound, and we utilize suitable solvents and we convert them into liquid, and then during that liquid formation, we follow some kind of reaction so that some stable metal organic compound is formed, and then that metal organic compound is either converted into a precipitate by using another material, or that metal organic compound is deposited on a surface. So it depends on what outcome do we require. If we want a thin film, then we can go ahead with that metal organic solvage. And if we require sorry, if we require a powder or a material, then we can go with precipitation. So it depends on our choice. So for that purpose also we utilize some other extra compound. And from sol gel method, we can have either the powder or a dense ceramic or a thin film. It depends on how we proceed. So this was the, say, general idea of my talk, or in a way it was the methodology which I am utilizing in my research work. So since the conference is on research methodology, so this sol gel methodology can be, say, a very special methodology when it comes to conduct research work within the limited circumstances with a very cost effective way. So now onwards, I'll be talking about some results based on the research work that I've carried out in my laboratory. So I've talked about co-doping. So here I'm talking about a particular system. So zinc oxide has been doped with aluminum and silver simultaneously. So what is happening? So these are the traditional characterizations of X-ray diffraction. It gives an idea about the structure or a phase of the material, because Sol-Gel method is an indirect method. We obtain a method following a chemical reaction. We obtain a material final outcome by following a reaction. So at the end of the reaction, whatever material we achieve, we need to check whether the proper phase has been formed or not. So X-ray diffraction is the most primary technique that gives an idea about what phase is there of that material. So phase means internal structure I'm talking about. Here phase does not mean that liquid phase or a solid phase or a gaseous phase. So not those macroscopic properties, I'm talking about microscopic properties. So X-ray diffraction pattern, we can notice this is the research work based on thin films. We can notice the single crystalline film formation, and the intensity of this X-ray diffraction peak is going down as the amount of dopant and co-dopant is increasing. And these are atomic force microscopic images. So that gives an idea about the surface behavior of the film, so thin film. So I'm specifically going to talk about this particular result. So surface roughness was seen to vary as the amount of dopant and co-dopant was getting changed within zinc oxide structure. So what is happening? Surface roughness is getting impacted. So as aluminum is getting introduced into the material zinc oxide, so surface roughness is increasing, and the moment co-dopant comes into picture, the surface roughness goes down. So here it creates a possibility of having the control over surface roughness. I attempted this study uh, for multiple times. Every time, this is one result, since this result has been published, so I'm showing it here. But multiple times repeated the same exercise, we found that surface roughness was getting reduced by the presence of uh, co-dopant. So surface roughness control, that can offer a very special feature, and that feature is because surface roughness governs the hydrophobic or hydrophilic nature of any surface. So hydrophilic means the water content is getting attached to the surface, and hydrophobic means water is not showing affinity to the surface. So here one particular picture of lotus leaf. So on lotus leaf, when we put water droplet, so it doesn't stick to the lotus leaf and it leaves and it rolls down. So this surface is called as hydrophobic. So hydrophobicity has multiple benefits. Today's industry is hugely demanding hydrophobic coating. Just I would like to give one example. We all utilize this tomato sauce. So tomato sauce, it is very difficult to extract out whole tomato sauce from the bottle. So if imagine if the inner surface of that glass bottle in which that tomato sauce has been kept is hydrophobic in nature. So that means the tomato sauce will not adhere, will not touch the inner surface of the bottle. So it will be very easy to take out the whole tomato sauce or to utilize the whole tomato sauce. So currently, huge amount of waste is being created. Same is the case with the toothpaste. We are not able to utilize the whole amount of toothpaste. So imagine if the inner surface of the toothpaste tube is hydrophobic in nature, so it will automatically come out or will be utilized. It will not stick to the inner walls. So by controlling the surface roughness, we can have the say creation of hydrophobicity, and that can eventually lead to a very big technology as per the industry demand. So that's the say general outcome of this particular research, even though I have not tried for, because food and these things, they require some kind of other studies also. You can create a hydrophobic surface, but it is whether it is good for say food material or not, so that also needs to be checked. So this is just a primary idea. And then I attempted a study where aluminium was utilized as a dopant and cerium was utilized as a co-dopant. So I'd like to now show only crux, or say very important results. So these were the powders, and X-ray diffraction is showing the multicrystalline behavior, and here it is WH plot, which is called as Williamson Hall plot. So we extract some data from X-ray diffraction and we plot a graph. So it gives the idea about the strain, how much micro strain is available within the given material, and also it gives the average crystallite size. So that calculation was done. So all of them were lying in the nanocrystalline regime. So quickly, I'm going to talk about another result. So here it is the band gap variation. You can notice as the amount of cerium is increasing into aluminum doped zinc oxide, what is happening? Band gap is slowly going down, and beyond a certain limit, it goes rapidly down. So control over the band gap. If we look at this graph, it shows a very precise control over the band gap by utilizing a suitable co-dopant. So control over band gap is essential. Initially, I was talking about photocatalysis. So control over the band gap is very important when it comes to utilize the material for particularly photocatalysis and many other optoelectronic applications. So this is the outcome of the utilization of co-dopant, cerium co-dopant into aluminum doped zinc oxide. These are scanning electron micrographs and photoluminescence behavior. So all these things were also getting affected. So I'll not talk much about them, and we'll pick up another set up another system. Here you can see europium has been doped into zinc oxide along with lithium. So you can say europium is a dopant and lithium is co-dopant. So europium and lithium, when they are simultaneously present, so here in particular photoluminescence character was getting influenced by the enhancement of europium. So europium was continuously increased, 136. These percentages, atomic percentages, they represent the change in the europium concentration, whereas lithium was kept at constant amount. So photoluminescence, you can see all the photoluminescence spectra are showing multiple emission peaks. They are lying in close to UV region, and also they are lying in the visible region. So all of them are, their intensities are getting impacted to some extent. So intensities are getting impacted, and which peak corresponds to which energy level transition. So that has been shown here. Another interesting part of this study was the band gap and microstrain. They both were seen to follow the similar pattern of the variation. So microstrain is a, say, mechanical feature, and band gap is an electronic feature. So they both are getting governed together. This study was also repeated several times, and some kind of correlation was there, even though we are still in the process of understanding or finding out some exact correlation. But yes, correlation was there. The way band gap was varying, alongside the strain was getting varied. So mechanical and optical features, they both are correlated. So this feature is particularly useful in, say, some mechanical devices where we want to govern the the optical properties by controlling the mechanical features. So here luminescence was also seen to be dependent on microstrain, and these are the electron microscopic images of the samples, which they were also showing various kinds of say variations. So now the last thing, we utilized cobalt as dopant in titanium dioxide. So these are the conventional, say, characterizations, X-ray diffraction, and in particular, we found that the cobalt amount of cobalt was available in two electronic stages. So how much is the contribution? So that can be identified by X-ray photoelectronic spectroscopy, and these are the Rietveld refinements. So those who are doing X-ray diffraction, they must be knowing about band gap. So band gap here was also seen to be reducing by utilization of cobalt in the matrix of titanium dioxide. So these were the theoretical studies. Density functional methods were utilized to calculate the energy band structure. So they were verifying the variation of the band gap. So these are scanning electron micrographs. Yes, on this particular part, I would like to focus 1 minute, and then probably my talk will be concluded. So ferromagnetic character was noticed in titanium dioxide by the utilization of cobalt as a dopant. So if we notice these three curves particularly, so if we notice, we find that in high magnetic field region, the behavior is paramagnetic. Only in a small zone it shows ferromagnetic character. So pure titanium dioxide or undoped titanium dioxide has very weak ferromagnetic ordering. But as cobalt goes inside it, so ferromagnetic order is getting increased. So this is the enlarged view. This particular graph is the enlarged view of this zone. So you can see the hysteresis loop, and it is demonstrating the ferromagnetic character. And then again, when cobalt is beyond a certain limits, then paramagnetic character has been resumed. So this 3 atomic percent cobalt dope is showing highest ferromagnetic ordering, and it is because of the BMP formation. So BMP is bound magnetic polaron. So there are two popular models to justify the magnetic behavior in diluted magnetic semiconductors. So one is RKKY model, and another one is bound magnetic polaron model. So we utilized this bound magnetic polaron model, and we calculated the effective magnetic moment. And when we plotted the curve of the experimentally obtained magnetization and I'm sorry, magnetic moment and the magnetic moment obtained from this relation, so they both were found to be following the same kind of track. So that means this bound magnetic polaron model, and it is actually based on the connection or interaction between the defect and oxygen vacancies, particularly in different states. So this model was able to justify that yes, magnetic moments are based on the bound magnetic polarons, and they are responsible for creating the ferromagnetic ordering, high ferromagnetic ordering in cobalt doped titanium dioxide. So in overall summary, we can say that doping and co-doping, particularly in wide bandgap semiconductors, is highly useful. It can give an avenue of bandgap tuning, which is very much required in, say, optoelectronic materials and microstrain governed optical properties. So it creates a correlation between mechanical and optical properties. Photoluminescence, any material which has the capability to emit light, so that can be controlled and governed by monitoring the amount of dopant and co-dopant. And at the same time, the magnetic properties can also be governed and can also be say controlled by monitoring the amount of dopant and co-dopant. And all this is possible by a very cost-effective processing. So cost-effective processing, because I have already mentioned that I focus upon sol gel method, which is a very frugal method. So very fundamental properties like band gap, microstrain, luminescence, these are very fundamental character of semiconductor materials, they all can be understood, they all can be analyzed, they all can be experimented with the help of a very cost effective process, that is sol gel process. So that's all about my talks. I would like to express my sincere thanks to my PhD student and my collaborator. PhD student is Mr. Ashok Kumar, who has recently completed his PhD, and Saikat Chattopadhyay is my colleague, and also the financial assistance provided by UGCDAE CSR Mumbai Center. So with this, I must say thanks to everyone who is available on this platform, and I'll be happy to answer a few quick questions if anybody is having.